Hey everyone, if you were absent or just need to kind of come back to the atmosphere lesson, this is it. I'm going to try to keep it pretty brief. So, the atmosphere is a layer of our Earth, just like our mantle and our crust and our core. Although those are rock layers, this is a gaseous layer. And it does more than just allow us to breathe and insulate heat. It actually does protect us from space debris as well and solar flares. So, whenever we see solar flares, for example, which is basically think like wind from the sun that's charged with ions and other particles coming straight at us. Our magnetic field, which is created from our iron core, our magnetic field comes into contact with it and, like a shield, blocks the solar flares from bothering us here on Earth. And the product of that are the aurora borealises, which are pretty cool. So, in the news, sometimes you'll hear about a really great solar flare up event, and that's producing a lot of aurora borealises that we can see further south. That's related. The other thing, protect us from space debris like meteors. So, whenever a meteoroid comes in contact with the atmosphere, changes its name to a meteor because now it's in the atmosphere, but it'll burn up because the atmosphere is filled with gases. Anytime that you have a fast flowing object like a meteor trying to bombard Earth, it passes through all those gases and creates friction, right? That movement, the rubbing with the gases in the meteor creates a lot of friction, which creates heat and ends up burning it. And for the most part, the majority of meteors burn all the way up. They become shooting stars. That's what we see. However, if there's one on the bigger side, it'll burn up, burn up, burn up, and then just a little bit will have made it through. And so we do get the occasional crater impact, but not as much as if we didn't have an atmosphere. So, for example, the moon has no atmosphere and it is littered with a whole bunch of craters because, again, it doesn't have an atmosphere. So, it doesn't have something to block that debris, to burn up that debris. Instead of it burning up, it just lands on the moon and now it's riddled with craters. So, it's a really awesome thing that we have our atmosphere. We have gases in here that we are able to breathe. And the gases too act as an insulator, which keeps us warm. And I think it's really neat that we have just enough atmosphere to keep us warm, but not enough to make us overheat, like Venus. Venus has a very thick atmosphere and it's incredibly hot. So we have the perfect kind of Goldilocks amount going on. Our atmospheric composition, a lot of people think that because we breathe in oxygen, our atmosphere is either only made up of oxygen or primarily made up of oxygen, but that's actually not the case. Currently, and I say that for a reason, currently the majority of our gas is nitrogen. And I believe it's 78%, and about 21% is oxygen. And then that last percent is a whole bunch of those smaller compounds as well. It hasn't always been like this, though. So we breathe in oxygen, we breathe out CO2. Plants do the opposite. They breathe in CO2, they exhale oxygen. So as we've started to see newer and newer types of life, we've been able to change our atmospheric composition. Before any life, we had a much different atmosphere. We weren't able to convert some of those gases to other gases and vice versa. We had a lot more volcanic eruptions. It was a lot more destructive. Think a lot of lava. We're still developing our atmosphere, all of those different things. So the compounds were much different. Well, as life slowly began to evolve and we're able to convert oxygen into CO2 and vice versa and whatnot, we've been able to transform what our concentration of gases looks like through a lot of those photosynthetic organisms and then later on the mammals and whatnot. So it has changed over time. It will continue changing as well. It's a lot more, I would say it's a lot more stable now because we haven't gone through the kind of like the birth of Earth. We're kind of in those adult stages now. So I would say it's a lot more stable, but you never know. So if we look at this graph right here, we can see this blue line stands for oxygen. The title is Oxygen's Content of Earth's atmosphere. So this blue line represents the amount of oxygen. And for a while, it's steady and very low. And then all of a sudden, there's a spike. And then it kind of flattens out a little bit. And then another spike. And then a huge dip. And another spike. And a smaller dip. So, what I am guessing just by looking at this data, not knowing anything about our geologic history, but if I'm just to look at this graph, I would assume that there has been an evolution of life right here, which has caused that spike of oxygen, and another one right here, and then maybe some kind of a mass extinction or big volcanic event to cause the oxygen levels to drop, but then come back up again and drop again. So by looking at the graph, you can interpret what may or may not have happened, but we have seen a lot less oxygen in the past and a lot more in recent years. The last thing that we'll talk about are Earth's layers. There are two more slides after this, but they relate to, or not Earth's layers, the atmosphere's layer. So yes, the atmosphere is a layer of Earth, but just like the mantle, it can be broken up into smaller pieces, 5 pieces to be exact. Although some people kind of take away the fourth or the fifth, and I'll get to that. The first layer, if we're closest to the surface, is the troposphere. This, of course, is where we live. Weather happens here. There's a lot of water vapor. About 99% of all water vapor is here. So again, weather is occurring. Planes are able to fly at this altitude. And yeah, troposphere is the one that we're most familiar with because we live here. Then we have the stratosphere, and this is known for housing the ozone layer. That's going to be important in just a second, but I think we all know the ozone protects us from that ultraviolet radiation, so that way we're not being, every time that the sun shines, we're not feeling the effects of the ultraviolet, which gets into your cells and can actually damage your cells. Some does get through, but it blocks a lot. Then in the middle layer, we have our mesosphere, which is where meteors burn up. And if you notice, I tried to emphasize all the M words because our middle layer has a lot of the M's, and that's how you can remember it. After that, we have the thermosphere, which is known for our aurora borealises. So at this altitude in our atmosphere, that's where our magnetic field comes into contact with the solar flares. You can kind of think like this is the extent of the magnetic field, if you will. And some people do, they don't include the exosphere within the layers. They kind of think like this is just space, but others do. So it's on here as like a just in case. But this is where we have a lot of our satellites and spaceships and whatnot. Some consider it, again, the last layer before space. Others just consider it space after this point. But it is, I like to think exosphere, exit to space. So it is kind of easy to remember that, the name meaning. So pressure in the atmospheric layers throughout, doesn't matter what part of the atmosphere you're in, throughout, as you move up in altitude, you're going to reduce your pressure. And the reason why is because if you were to imagine a column of air sitting right above you, that air, I know it doesn't feel like it, but that air has weight. It doesn't feel like it because we're used to it. We are born here and we've constantly had this pressure sitting on top of us. Sometimes, though, the pressure can change on the surface just a little bit, and we'll talk about that. But primarily, as you go up into our atmosphere, you're now at a higher elevation, so you have less air on top of you. There's air below you, but it's not pressing on you because it's below you. So now you have less on top of you when you're higher up. And so you'll feel the change in pressure by your ears popping when maybe you are flying in a plane or driving up a mountain or something like that. Your body is trying to equalize this new pressure because now there's less weight on top of you. So pressure decreases as you go up. If this is hard to visualize, think about the opposite. Think about going super far down. And I'm talking about even like below the water level. So if you've never swam in the ocean before, I'm sure you've probably swam in a pool before or a lake or something like that. As you try to dive down in that water, you're going deeper and deeper, and now you're under more and more and more water the further down you go. If you've ever tried to pick something up off the bottom of the pool, you know it can be quite difficult because, again, now you have all that pressure sitting on top of you because you were further down than you were before. So it can be a little hard to swim. You feel the pressure in your ears too, and so you often have to come back up just to, you have to breathe, but to stop feeling that pressure, you would resurface. So if you are able to know that feeling, then again, you'll be able to understand as you go down, you get more pressure. So therefore, as you go up, you get less pressure. So you can use that as an example. And then finally, temperature in the atmospheric layers. So we actually did an activity on this. Please message me if you have any questions. The paper is in class. But what the activity is trying to show is a visual representation of how temperature changes throughout the atmosphere. So I'm just going to explain this to you now because you're watching the video for help. In the first layer, the troposphere, we're going to decrease our temperature as we go up. I know this seems self-explanatory because we live here on Earth, but the main reason is because when the sun heats up the Earth, land and water heat up more effectively than air does. It simply like passes through the air, if you will. But land and water absorb the heat a lot better than the air. So on the surface, it's a lot warmer. As you go up in altitude in the troposphere, like for example, climbing up a mountain, it gets colder and colder and colder. Some of you may remember that a lot of our mountains are capped in snow longer than places that are further closer to the surface, closer to sea level. So as we go up, those locations are now surrounded more so by air than they are by land. And so it's going to be a lot colder as you go up. However, once you get into the stratosphere, that changes. And the reason why is because the stratosphere houses the ozone layer, and the ozone absorbs and reflects ultraviolet radiation, which is a form of energy. And energy can translate to heat. So, because it's absorbing that energy and reflecting that energy, we're seeing an increase in temperature, an increase in energy, an increase in heat in the stratosphere because it houses the very thick ozone layer. Once we get into the mesosphere, though, we see the typical drop in temperature again. Now we're further away from the ozone, and there's some different gases in here that work a little differently. Finally, in the thermosphere, we see a great increase again, but the funny thing is it doesn't feel this hot. It's showing that we are over 140 degrees Fahrenheit or over 60 degrees Celsius, but I think more of us are familiar with Fahrenheit. It's showing that this top layer is extremely hot. However, if we were to actually go there, it would not feel this hot. And the main reason being is all of these gas particles are really scattered at this point. They're a lot more concentrated the closer to the surface you are, but as you move away from the surface and you get to the outskirts of our atmosphere, those air particles are so much farther apart. Now, what heat is how quickly molecules move. So if it's cold, it might vibrate just a little bit. But if it's hot, it's moving a lot. So the hotter something is, the more it moves. Well, because the particles are so far apart, yes, they're moving a lot, but they're not close to each other. So you're not able to feel the heat of the particles because they're not close to each other like they are on the Earth. So that's why it's showing that it's hot. The particles just have a lot of energy. You can think the aurora borealis, it has our charged particles, our ions that's coming into from the sun. It's coming into contact with our magnetic field. So we have these like charged particles, but the particles are so far apart you don't feel it. That's why the sky is black at this point, not blue anymore. We have this transition from blue to black as the particles get further and further and further apart because it's not bouncing the light off as effectively because they are farther apart. So hopefully that makes sense. Main thing here is just that there's this zigzag pattern when it comes to temperature. And if you can remember, which I think we all can, that as you go up in the troposphere, temperature drops. Well, then zigzag is telling us that if it drops in the troposphere, it raises in the next, and drops in the next, and raises in the next. So you can remember it that way. It zigzags, starts with a decrease first in the troposphere. And that's, I think, all that I have for you guys. So if you have any questions, just let me know. But that is the atmosphere lesson.